Hello. So in this notebook, I'll be talking about the hyperparameter tuning for deep learning. So, and in we will also look at the best parameters for your deep learning models, and how it makes your model perform better. And first, we will discuss what hyperparameters are and why they matter, then manual tuning strategies and intuitions, automated search methods, and modern tools, and best practices for efficient tuning. So let's look at what are hyperparameters. So hyperparameters are the parameters to your model which you set before training, and whereas parameters are the features which are learned during the training. So hyperparameters examples can be learning rate, batch rate, basically the configurations of your model can be considered as hyperparameters, and these are chosen by you, and they are typically less in numbers, typically around 10 to 50. And why it matters is the same architecture with different hyperparameter can give 90% accuracy with good hyperparameters, 60% and 60% accuracy with bad hyperparameters, and a complete failure with terrible hyperparameter. So hyperparameter tuning is often more important than architecture design. So that is why we are looking into it. So in the this first part, this defines a small tool, simple neural network, and it trains it 5 times with different learning rates, 0.0001 to 0.5, and it records training loss and validation accuracy for each run. So the left side is the training loss, and it's in log scale. So it shows that the learning rate of 0.001 and the learning rate of 0.01 excuse me, and so you can see how it smoothly converges, while the very low learning rates barely move and the very high learning rate are unstable. So, and the right one is the validation accuracy. So the same architecture models, but final accuracy varies widely depending on the LR alone, and it drives home the core point that hyperparameters matter as much as architecture. So yeah, then the key parameters is so they are categorized into optimization, architecture, and training. So for optimization, we have learning rate, batch size, optimizer, and weight decay. And learning rate has a very high impact on your model. And then we have architecture. It can be hidden layers, hidden units, dropout rate, and activation. And amongst these, the hidden layer has very high impact on the performance. Then we have in the training category, we have epochs and LR schedule, and they both have medium impact on the model, but these are also considered as hyperparameters. And now this code generates 4 conceptual visualization using simulated or synthetic data, not real training runs, to illustrate key hyperparameter trade-offs. So now this learning rate versus accuracy, it's a bell curve shaped plot showing there's a sweet spot around 0.001 0.001, and too low is there is no learning, and too high we will have instability. So this is the sweet spot to keep the learning rate within these range. Then we have batch size trade-offs. Then it has dual axis bar plus line chart. So the larger batches train faster. This is the training time, this is the batch size. So larger batch size train faster but generalizes slightly worse. The red is the generalization, but the generalization is worse. So yeah, this is this. So this is the well-known trade-off. Then we have variance trade-off. So training versus validation accuracy as model complexity grows. So at a certain point, the points diverge, and that is the overfitting zone. Then we have hyperparameter importance. So this is the horizontal bar chart showing learning rate has the highest impact. And then we have batch size, depth, width, dropout, and other. But learning rate plays really important role. Then let's move to the manual tuning strategies. So like the learning rate finder. So we will start with the learning rate. It's the important. The strategy is gradually increase the LR and watch the loss. So if the loss decreases, the LR is in good range. If the loss explodes, the LR is too high, and if the loss barely moves, the LR is low. So you have to increase your LR. So this is a basic strategy which we use. So in the code implements the classic LR finder technique, and it starts training with the tiny LR and then exponentially increases each step, recording the loss if it stops when the loss explodes. So let's look at the chart. Yeah, so it's a log scale plot of LR versus loss. The code finds the point of a steepest loss decrease and marks it with a green vertical line as suggested learning rate. So the idea is pick a value below that point for stable training. So that is how we find out it, by manually tuning it. Now let's look at the grid search. So grid searches try every combination of hyperparameters. So let's say we want to try these LRs and these hidden layers. So we just create a grid out of it with every combination. So this is like 3 into 3. So 9 combinations we got. And then we train the model on all these combinations. The pros are it has complete convergence, but cons is exponential growth. Then pros is it's reproducible and easy to parallelize, but consequences are it wastes time on bad regions and requires good grid design. The code performs an exhaustive 2 into 4, just 12 combination search. 12 combination search over LR rate with 0.001, 0.01, 0.1, and hidden grid as 16, 32, 64, and 128. So each combination trains a model for 50 epochs and records validation accuracy. Now, so it prints the accuracy for each hyperparameter combination which we had. And here you can see the this one is the best, which is 99% accuracy. Excuse me, which is LR 0.1 and hidden layer 64. So that is the best hyperparameter. So we can go ahead with this one. Then we have random search. For random search, the key insight is for most problems only a few hyperparameters really matter. So random search explores more values of important features by chance. So the research findings are random search is more efficient than grid search in a high dimensional space. With the same budget, grid search has 9 points in a 3 by 3 matrix grid. Random search has 9 different values for each parameters. So the code produces two outputs demonstrating why random search is often superior to grid search. So this is a conceptual diagram. This is a side-by-side scatter plot. Excuse me. Comparing grid versus random search in a 2D hyperparameter space. So the key insight is grid search tests only 3 unique values on important hyperparameter, while the random search tests 9 different values with the same budget. And then we have random search results. So the random search runs 20 random trials sampling LR on log uniform scale, and hidden size as a power of 2, and the dropout as 0 from 0 to 0.5, and it prints progress of each for every 5 trials and reports the best parameter combination, hyperparameter combination. So the key insight over here is the random search covers more unique values, and if only hyperparameters matters, random search tests 9 values versus 3 combinations. Yeah. Now then we have Bayesian optimization. So this is smart search. So Bayesian optimization learns from previous trial to suggest better points. So how it works is you build a model of the objective function, which will be a surrogate model, and you use it to predict a promising region and balance exploration versus exploitation, and then you update the model after each trial. So the key concepts here are, surrogate model, which will be a Gaussian process or a tree parsing estimator, and acquisition function, which decides where to sample next, and excited improvement, common acquisition and function. Then we also have Optuna. So Optuna is basically a state-of-art hyperparameter optimization framework. So it has automatic pruning of bad trials, efficient sampling or algorithms, and it has a very easy to use API, and it gives great visualizations as well. So this is the code. The code uses library to run 30 automated trials. So the objective function samples 4 hyperparameters, which is learning rate, hidden size, dropout, and number of layers. So and builds a dynamic model which trains on 50 epochs and uses pruning to stop bad trials early. So how pruning works is if a trial is performing below the median of other trials at the same epoch, Optuna stops it early using median pruner, and it saves significant compute time. Now we are, these are the number of trials running. We have 29 trials, 30 trials running, and it gives the best accuracy and all the 4 best hyperparameter values after the 30 trials. Yeah, so the best accuracy and these are the best hyperparameters, and dots for each trial's final accuracy. Now this is the Optuna optimization history. So these are the dots for each trial's final accuracy, with the red line tracking the best so far. So these are the best one, which is 99%, and the right hand side is a bar chart computed by Optuna showing which of the 4 parameters most influenced the accuracy. So yeah, basically it's data driven, based on actual trial results and not hypothetical. So yeah, it gives a really good results. Now let's look into the best practices. So for best like um, like efficient tuning strategy would be start simple, use defaults, and ensure the code works. Then you find out the learning rate, use LR Finder or course search. Then you tune important parameters first, which is LR batch size, and then look at the architecture. Use random or Bayesian search to more efficient, which is more efficient than grid search, which is a very repetitive uh, method. Then use early stopping, so you don't want to waste your time on bad configs. And then scale up gradually, so start small, increase budget for promising regions, not for all run. And these are some common mistakes to avoid, which is tuning on test data. Why it's valid leads to data leakage, so always use validation set. And we have two wide ranges, so which wastes trials, so start narrow and then expand. Then ignoring interactions, so missing good combos. And the best way to handle this is use Bayesian optimization. And then we have linear search for learning rate, which leads to wrong scale, so use log scale. Then we have no reproducibility, so you can't repeat results, so set random seeds. So yeah, that is pretty much in this hyperparameters tuning notebook. Thank you.